you cannot imagine how many conferences I've had here that were not about Anderson localization. Okay, it was about medical imaging, it was about geophysics, and on Friday, this day, the last day of the conference, everybody was talking about Anderson localization. So this is something that happened very, very often. So, and now that you have come here to talk about Anderson localization, you are now part of Hotel California. You will know that. You will find out later. Okay. Before I want to say something scientific, I want to make a tribute to Phil Anderson, because last time I talked in this, the last time I joined Simon's collaboration meeting that was in New York City, it's just before lockdown, and in the meantime, Phil Anderson died. This is a painting that apparently was in his office in Princeton. This is a painting. The author of this painting is not known, but you can see on the painting it's the garden of Phil Anderson. It's called the Garden of Phil Anderson, and you see all his great contributions here in the garden: the Anderson localization, the spin problem, the spin Hall, and so on. So all the great things you can see here. And of course, Phil Anderson contributed a couple of things to physics. It's quite impressive. Of course, his paper, Anderson localization, the first one, and 3 other ones. He not only created Anderson localization, but he also made the major contributions, especially the many-body localization and the scaling theory of localization. But arguably, these are not his major contributions to physics. And my personal guess is his major contributions to physics was made a little bit later. First, when he discussed, before the Higgs mechanism was introduced in high-energy physics, he introduced the spontaneous breaking of U1 symmetry for superconductors, where he explains that this is a very easy way to explain the Meissner effect, and you get the Joseph effect for free. Okay. And there is another thing. If you haven't read this paper, then you really should do it, especially the young people. More is different is the psychology of science. It is about reductionism. Can we have one fundamental equation that describes everything? Phil Anderson says no. There is something like complexity, and there is something like emergence. And he defines it very well, and he says that if you go on higher scales, things become more complex and different laws will emerge. And he defined this way complexity very well. And if you mix the two discoveries together, then you get what Jerry mentioned in the last seminar, that you get the spontaneous symmetry of replicas, and that in the complexity that was explicitly mentioned in the Nobel Prize of Parisi. And then, arguably, there is even more what is important for Phil Anderson. It was when he was asked to give his opinion about the development of the supercolliding superconductor in the United States, and he was very much against it, and he had arguments that he had written down, arguments that I can transmit again and that you can use because it is so much true. Because Anderson believed that, you know, the amount of money that you spend to crank up more and more the energies of the supercolliders, you know, you should more spend money to low energies, condensed matter physics, for instance. And he argued, for instance, that science can be fundamental without being irrelevant. So this is a very good thing to think about. And money can, of course, be used also for education. This is very important. And in this context, you can mention, I once estimated that if CERN would be cranked up by 1.1 in energy, then you blow the whole budget of Europe for 1 year in condensed matter physics. Okay, that's a little bit what is going on. His third argument was about this super colliding machines that are used to guide the elementary particles. And they said, well, these supercolliding things, you know, that we developed superconductivity, and it is just a spin of our work. And of course, Phil Anderson at the time, he was the world expert on superconductivity, and all the ideas actually came when he was working on superconductivity. And then finally, I think this is something that is very true for today, for the landscape model, for instance. The golden eggs are very seldom produced by the golden cheese. I think when the landscape was discovered 10 years ago or something, nobody was really talking about Anderson localization. It was certainly not the golden cheese. If you deposited an ERC or a contract, a national contract, Anderson localization, nobody will give money for it. And yet, in this context, you know, the golden egg, the landscape emerged. So, you know, Anderson was right again. Okay, so let me now come to more science and to the localization of light. Fabrice showed this equation already. So this is the Helmholtz equation. You see the Helmholtz equation, you see the Helmholtz equation, dielectric constant, speed of light, you see a double nabla, and there is a source here that I put in grayscale because the source should be there. There is an antenna who emits, and the antenna is this one, okay? And but this is not a correct way for a mathematician to write the equation, and I think this was also mentioned by Fabrice. One way of writing it is to define a new state vector, which is basically the square root of epsilon times the electric field. Then you have another time evolution operator that you can call k, and this k is the square root of epsilon on both sides of this operator. And if you now look at it, this is a vector equation. Okay, still a vector equation like the Helmholtz equation. You have a time operator that is Hermitian, and it is positive definite, okay, because p squared essentially is a positive operator, like the in Schrödinger operator. However, there is one thing that is very important. It has an infinitely degenerated zero eigenvalue, and these are the longitudinal waves. Okay, because if you a little bit forget about epsilon, you see immediately that everything what is parallel to p has zero eigenvalue. Okay, so you have an infinitely degenerated zero eigenvalue. And it was mentioned that there was a problem of defining a landscape with electromagnetic waves. And Fabrice told, well, this is a vector wave, it's complicated and so on. I think the most important problem with landscape in electromagnetic waves is not that it's vector. The direct equation is vector as well. Okay? It is simply that there is an eigenvalue 0. And it's 0. And if you put here 1, then you throw away the longitudinal waves. And the rest of my talk I will explain that in 3 dimensions you cannot throw away the longitudinal waves because they couple to the transverse waves. So I think that is the main obstacle for the landscape in electromagnetic waves. So let me define what I mean by longitudinal and transverse fields. To be clear, in real space it means for a longitudinal wave that the divergence is 0, and it's non-zero for some part in space, can be a charge for instance, and that the curl is everywhere equal to 0. Okay, that is the true for an electric field, for a longitudinal electric field. A transverse means that the divergence is 0 everywhere, and the curl is not necessarily 0 everywhere. That is the definition of a transverse field. The magnetic field is by definition transverse, but not the electric field. And if you look into phase space, where it is much more important for a theoretician, then if there's some point in space where the divergence is 0, then in k space you see immediately that it is for a whole dense set, and even for infinite k it is really non-zero. So that's a characteristic of longitudinal space, longitudinal waves. In phase space, in Fourier space, they reside at infinite k vectors. That is a very in theories that is a huge complication. And now there is this famous Helmholtz theorem saying that any field can be written as a sum of a longitudinal field and a transverse field. And that is a mathematical theorem. You can find the proof on internet. And so that is true. And you cannot really remove in the electric field the longitudinal waves because they are part of the complete set in Hilbert space, in electromagnetic Hilbert space. So you cannot just disregard them. Okay, now if we do a simple thing and we look in vacuum, so there are no dielectric constants, no charges and so on, then the transverse solution is easy. It is a plane wave, okay, and it has a polarization vector that is orthogonal to the k vector, and then you see the divergence is 0. And then you have the longitudinal solutions. They look like this, okay, and it is true for all k, it's a solution, and for all k, they have eigenvalue 0, okay, so they exist, they're solutions of the Helmholtz equation, but they have eigenvalue 0. Okay, now you can ask, you can say, well, these eigenvalues 0, do they really matter when I am at optical frequencies? Okay, this question, for instance, is I have a source. Okay, a source can be a dipole, a vibrating dipole. My vibrating dipole is here. It's the source, and then the electric field is the green function times the source. Okay, the green function you see here. It is decomposed into the different modes of the Helmholtz equation. So here you have the 3 eigenvalues, and you see in principle the longitudinal value contributes if the longitudinal wave function is not orthogonal to the dipole field. So if you do, for instance, a dipole that is almost a delta function, so now in Fourier space this guy does not depend on k, you can do the integral and you find something that everybody knows. It is a longitudinal field, but it's not, it looks like a static electromagnetic field, longitudinal electromagnetic field. However, I did the calculation at optical frequencies. So still at optical frequencies you see there is a longitudinal field. Okay, so it exists. There is one very important point in vacuum you see immediately, and that is true in condensed matter physics. It's a very important notion. The local density of states, or the density of states per unit volume, which is the imaginary part of the Green's function, it is 0, because you see there is an I0 here. If k is 0, this guy is never going to be 0, because I have optical frequencies, so I can forget the small imaginary part, it's 0. No longitudinal waves. They exist, but they have no density of states. And that is a very important motion. Now, if I go to a random medium, okay, so now I have a random medium, I have a Green function which is now given by the dielectric constant frequency and then this Hamiltonian, electromagnetic Hamiltonian. Now things are a little bit different, because if I now do the average over all realizations, I get something that is in physics called the Dyson equation. So I get a new Helmholtz equation, but now with what they call the self-energy or a mass operator. In mathematics it's called mass operator, and it depends on the frequency and on the wave number. Okay, so now you can see this is, because you average, it is a dissipative operation, so this guy has a positive imaginary part. This is very important, or a negative imaginary part. And now you can do the same thing. You can see, you can say, well, I calculate the imaginary part of the longitudinal Green function. This guy splits up into a transverse part and a longitudinal part. It's quite easy. And then you can see that if I pick out the imaginary part of only the longitudinal field, which is the longitudinal density of states, it is something that is non-zero. And of course, this corresponds to stock longitudinal energy, dipole-dipole coupling, and so on, in your random medium. Okay, and well, you can call it density of states or energy, it's the same thing. What is very important to note is that because it's a longitudinal field, the curl is 0, and the curl of the electric field is the magnetic field, and the magnetic field is 0, and therefore the Poynting vector is 0. Longitudinal waves exist, they have a density of states, they have an energy, but they do not propagate. That is very important. Okay? Now you can do the same thing for the transverse waves. The transverse wave, they propagate. So you see here something that propagates with an attenuation because they see a complex medium, a complex valued medium. They are transverse, the decay is 1 over r in 3 dimensions. And now you can see that there is a curl that's propagating in a direction of x. Okay. Okay. So this is a numerical simulation. So what you see here is a slab with thousands of particles, electric dipoles. So this is really what I'm going to discuss. So I have a random medium with dipoles. They have a very dense number density, very high number density. The number density per cubic wavelength is more than 100. So it's really very dense. They would be Bose condensated, but of course they don't know here. But it's very, very dense. And now you average the field. So now I send in a plane wave and I calculate the average field, which would correspond to the solution of the Dyson equation. Okay? And what you see here is the real and imaginary part of the transverse waves. I remarked that in the numerical simulations it's very difficult to see the longitudinal waves, but you can easily see the transverse waves because they propagate. And they decay with a mean free path, and they oscillate with some effective wave number. And well, what you can see from the real and imaginary part fit is very well, and from that you can get k, you can get the mean free path, you can multiply, and it is 1/10. Okay, 1/10, mean free path type wave longer. In 3 dimensions, the argument is always that around KL equal 1, something like localization should occur. This is true for electrons, this is true for elastic waves, and the question is this a localized sample? I will come back to this, but at least we have exact numbers, we have a wavelength, and we have a mean free path. So now, what happens in usually transport theory? Because we are not interested in the average wave, we are interested in the average probability density or the average energy. Now, the standard thing that you do in electron transport is the probability at some detector to find the electron is proportional to some kind of source and some kind of operator, which is called the quantum probability density in condensed matter physics. So this is the thing that we want to calculate. Okay, and there is a whole bunch of theory for that. Of course, we know that this quantity obeys more or less a diffusion equation because that gives you ohmic transport, okay? But in the presence of localization effects, there is this equation that was published 20 years ago. It's a very simple equation. You see here again the diffusion equation, okay? And then you see the diffusion constant, that is some constant. And then there is a correction which is due to quantum effects. The quantum effects I will not, it's quantum interferences, it's weak localization and so on. And the equation tells you that the diffusion constant is renormalized by this object, which is called the quantum return probability density. It's very well described in a book by Montambeau and Erik Ackermans. So what the result of this equation is that the solution of the diffusion equation determines actually the diffusion equation, the diffusion constant itself. So you have a self-consistent problem. Okay, but it's a very simple equation, and you can solve it almost analytically for very simple cases. In an infinite medium, it puts the mobility edge at KL equals 1. You can easily do the calculation. And for other systems, for one dimension, you get localization, exactly the thing. And I will give you one example where it is really non-trivial, because in an infinite medium, of course, this object does not depend on where you are, because every point in space is the same thing. However, in a finite object with open boundaries, this one depends where you are. So deep inside the medium, you can forget about the boundaries because it's almost infinite. But if you are close to the boundaries, then a lot of quantum probability will disappear in space and will not come back. And this one will be very small, and the renormalization will be negligible. And this is what then happens. Is I have a waveguide here. Okay, I send in waves. So you don't see it here, but it's really a waveguide with boundaries. So this is really what is the tool in mesoscopic quantum transport. Okay, here it is just numerical simulation, exact numerical simulation of scalar waves. You have a source, and you solve Maxwell's, not Maxwell's equation, this is scalar wave equation. You solve it exactly, okay? This is a numerical simulation with 10,000 particles, so you can easily solve it. And then, for instance, you can calculate the local diffusion constant, which is the current divided by the gradient of the energy density, which is the D. And what you see here as a plot, the position inside the tube, and here you see the diffusion coefficient. The straight lines is the prediction, the analytic prediction of this diffusion equation in the self-consistent theory. Okay, everything is localized in the waveguide. We know that if the waveguide is sufficiently long, all states are localized. Okay, but if the length is comparable to the localization length, it is not. And what you see here is the exact solution and the numerical solution of the diffusion equation. They fit very well for different lengths, etc. And you see for big lengths, I mean, the suppression is very large in the middle and almost negligible on the sides. And this is what I was saying to Vincent the other day. This could be a quasi one-dimensional picture of your atomic cloud. The diffusion coefficient is localized deep inside, but it's not outside. So this is maybe something that you should take into account when you try to interpret your models. Okay, so let's now go to electromagnetic waves. Electromagnetic waves, you have a source, and you have an antenna where you measure something. And the same thing can do for electrons, with the only difference that the electric field is a vector. Okay, so now you calculate, let's say, the polarization correlation function at the detector, which is a source convoluted with an object. And this object by definition is a 4-rank tensor. It's by definition. The source has 2 components, and the object has 2 components. So the guy who links the two has 4 components. So this is thing. And now, if you do the numerical simulation again, the same slab, you send in a plane wave here, and you look how the energy density decays in the medium. So the energy density, which is essentially the electric field squared, you look at it comes. So here you see the plot as a function of depth, energy density. So this is the solution of the normal diffusion equation, the black line, and this is the exact numerical simulation. So we have the exact situation of the KL is equal to 1/10, and you have more than 100 dipoles in a cubic wavelength. So it's a very dense system. So everybody would say this should be localized, but it's not. You see that the normal diffusion equation with no renormalization whatsoever, it's just Ohm's law. This is just Ohm's law. This is an ohmic conductor, and the conductance scales just like an ohmic conductor in a trivial way, and the energy density just decays linearly, and from the slope you can get the diffusion coefficient, and You can go back home, finished. There is no localization whatsoever. So this is strange. You have no localization in a system where we always believed things should localize. And this means somehow in our description of localization, something goes wrong. What is when we apply the electron theory to electromagnetic waves. And the difference is, of course, the longitudinal wave. But how does it come in? And to understand how this comes in, we have to really go back to square one. And square one is the Einstein-Kubo approach to diffusion coefficient and to transport of waves. So what happens if you look at an excitation in condensed matter for an electron? An excitation is characterized by an energy and a momentum, and you look at the correlation function, you average, okay? And there is a difference here plus q and minus q. This q is not at all of the size of the wave number here. This is a macroscopic wave number, so you look at long scales. If you Fourier transform, you mean that the Fourier transform of this guy is the transport from here to there. Okay, it has nothing to do with the cycles. If you do this correlation function, if q equals 0, then there is a mathematical theorem saying that this correlation function is equal to the imaginary part of the green function that you recognize as the spectral function. This is a theorem. It's always true no matter what, and it has to do with, of course, equipartition in phase space because of the multiple scattering of the waves. And then the Kubo theory is always a linear response theory. So you put a small gradient and you make the perturbation in Q. Okay, so you get something linear in Q. And because you have average over everything, you have on average rotational symmetry. And if you have on average rotational symmetry, you should have a dot product between P and Q, because there is no other scalar that has rotational symmetry which is linear in Q. So this is just exact, okay? You can think about Q squared, but we don't do that. It's linear response theory. And what remains is an object G0, okay, that you have to calculate. And it is not easy to calculate, I can tell you, but all books in condensed matter physics, they calculate it. If you do the Drude approximation, for instance, it is well known that this guy is this guy squared. So this guy has a lot to do with the spectral function again, okay? But it's not the spectral function, but almost. Now, if you take this one and you calculate the current is the first moment in P of this object of this correlation function. Now, the first thing drops out because it's isotropic, and this one remains, so you get a current which is proportional in real space to a gradient, and the constant of proportionality is the diffusion coefficient, and if you read off, you see that the diffusion coefficient, or more precisely, the conductivity, is given by the integral over all P of this object that I have to calculate, and then P squared. Why is it P squared? Because it's current correlation function, as Thierry mentioned this morning. Okay, so this is well known. This is an exact formula. Okay, there is no approximation whatsoever, and you see that if D has to be 0, then this guy has to be 0 for every momentum. Okay, because I cannot imagine that only the integral is 0. This must be 0 for all P, and it's a very strong statement what I do. It is much stronger than just saying that the diffusion coefficient is 0, which means that this whole distribution in P space that I think with cold atoms you can measure, there's something happening here that is very weird. Now, if you do it exactly for the electromagnetic Vector function, there is a slight difference. You look again at exactly the same correlation function. Okay, you have an excitation with frequency omega and wave number p, and you look at the correlation function plus and minus q, you average. You get, again, the theorem, you get the green function, but now with two polarization indices. Okay, fine. This is exactly the spectral function in phase space. You get, again, something linear in q. Okay, but now, because you have a second rank tensor, it's like the matrices, the Pauli matrices. You have four different possibilities. And now this object G, you can easily see that this object G, it is a second rank matrix, and because it's linear in Q, it must be Hermitian. You can easily read it off. It must be Hermitian. If I switch I and G and take complex conjugate, it must be Hermitian. So I essentially get the four Pauli matrices here, but I don't write them as the Pauli matrices. I want to write them as a pure transverse part, a pure longitudinal part, and then two parts which look like a mixture of transverse and longitudinal parts. So this is just no calculation, it's just symmetry. Just you have something linear in Q. It must be rotationally isotropic. Everything is rotationally isotropic, and I have four different possibilities. And that's all. So now if I want to solve transport of electromagnetic waves, I have to solve this one, this one, this one, and this one. You see, it's much harder. But I don't want to calculate everything. I want to calculate pointing vector, because that's the current. I calculate the pointing vector. It's easy, because I can take the curl from this guy, and I can take the curl again. And then you see that this is going to be proportional to the gradient, because the first term drops out. And I get something, diffusion coefficient. And now I get the exact Kubo formula for the Einstein-Kubo electromagnetic conductivity, which is again an integral over P. And what you now see, this thing drops out, because I have to take the real part. It's a little bit trivial, but it's true. I mean, the pointing vector is the real part of E cross B cross. So this one drops out. This one drops out because the curl is 0, so it trivially drops out. And this one just gives you what you always had. And then only this term comes in. So now you have two terms in the Kubo formula. One that is completely the one that you had with electrons, and then you have a second one. The conclusion of this equation is that you have two transport channels in electromagnetic waves. And there really are two channels. And if you take, for instance, Drude approximation, which is in all standard books, you get both of them. You get both of them. Now you can ask, if the diffusion coefficient is 0 here, then not only I have to calculate this one, be 0, but you have two things that have to be 0. Because I cannot imagine that D equals 0 means that this one is equal to this one, because the physics behind is completely different. Oh, I don't know, I might be mistaken, but it would mean that this one is 0 and this one is 0. And this is a true strong statement. And the rest I will show that this is actually impossible to do. So I can use again this self-consistent approach, because it was a very simple approach with lots of approximations, but it gives in most of the cases the right answer. What goes wrong in this thing? Now, what goes wrong in this thing is that now I have two equations with two unknowns, because this G, we know now in reality who determines the pointing vector, actually contains two waves, the longitudinal waves and transverse waves. So now I have the self-consistent equation. This is again my quantum return probability summed in phase space, and I have to solve this equation. It is 2 by 2 matrix now, and if I solve this equation, 2 by 2 matrix, you mean that there is something in the determinant down in the denominator. So I get something with the diffusion coefficient in the denominator. If I solve this equation, okay, I have to plug it back. That's the self-consistent problem in the Kubo formula, which is an integral of everything. And it means that the diffusion the denominator cannot vanish, because if it vanishes, the integral diverges. And this is very easy. If I now put as a solution the two terms again, so the normal one, which is purely transverse, and the second one that is a mixture of transverse and longitudinal, then I get an inequality that is to be respected. It means that the diffusion coefficient, or more, the electromagnetic conductivity, is bigger than some matrix element that I know exactly. Okay, and then here I get an interference term between the longitudinal waves and the transverse waves. Okay, and now you can see this inequality must be true for all momenta in the whole space, whole phase space. Now the longitudinal waves, as I mentioned earlier, they are everywhere. They are everywhere because they are delta functions in real space. So in momentum space, they are even at infinite p. The transverse wave, they only sit where the frequencies sit, okay? Because there is more or less a dispersion law. So the most stringent inequality happens when p is close to a mobility, close to a frequency omega over c. So, and then from that you can get an electromagnetic mod minimum, which I think never been predicted before. So I will now compare this to the numerical simulations, the same system as I had before. Okay, you see here the Joffe-Regel parameter, so the product of the wave vector and the mean free path that we calculate from the numerical simulation. So it's not input, no approximation, a very good fit. And here you see essentially the renormalization of the diffusion coefficient with respect to the ordinary Boltzmann value, which is here. Okay, the dashed line that you see, the dashed line is the mod minimum that you calculate just because there is an inequality for the diffusion coefficient not to be infinite. This is line, and the real lines is the prediction of the self-consistent theory. Okay, there are two lines. I will explain why there are two lines. The dots are the numerical simulations, so exact numerical simulations where the Thouless conductance is calculated with the scaling and so on. So we know exactly what the diffusion coefficient is. And you see that the agreement is quite nice. So different colors are different densities. So we have electric dipoles. So we have two free parameters. We have the density of the dipoles. It varies here for different colors. But you always also have the detuning. You can have far detuning from the resonance. You can have close to the resonance. You can have red retuning. You have blue retuning. If you have independent dipoles, that is well known that the Joffe-Regel parameter does not depend on left or right tuning because they have the same mean free path. But when you calculate two dipoles, it's no longer true. Okay, so that's why you see that even for a fixed mean free path, you get two curves, and you see also clearly in the experiments there are two curves in this plot. So the conclusion is there is no diffusion of electromagnetic waves in this cloud of electric dipoles, which is surprising, and we now have seen a way to understand that within transport theory. Okay, so I come to my conclusions. This is more or less the theory of white paint revisited, or maybe even suspended here in this case. There is an interference between longitudinal and transverse light modes that makes it impossible. You cannot localize both at the same time, and the interference between the two, the mix-up continuously in the diffuse transport makes it impossible to localize. And I mentioned a recent work that was done again by Sergey in collaboration with people who have a new software package in the United States, commercial, and they can calculate the same thing here with the electric dipoles, which is relatively easy to implement because you have to diagonalize a 10 by 10, 10,000 by 10,000 matrix, and I think I've seen worse today, yesterday. But here you calculate numerically the solution for n mesospheres, and with n mesospheres I mean you have finite size spheres, so you have not only 10,000 by 10,000 and 3 polarizations, but you also have all the multiples, so you have also 10 or 20 multiples to cope with, and so that is much harder. And it has again been confirmed that for these dipoles, for these mesospheres, there is no Anderson localization transition in 3 dimensions. So and this is probably true for the same reason. So I want to thank you for your attention. And